Okay, let's get started. Some announcement before the class. I emailed you, right, announcing your midterm exam performance, right? So it was a little bit, disappointing, and I feel like some of you are not fully understanding hardware-software interaction. For example, question number 3, I think DMA question. Scatter gather operation, right? So what I'm asking is, I want to see, if you understand the role of this hardware and the software. So what you have to do, what you have to write in software to do, scatter gather operation. So the thing is, you have to write, write software that that contains block description, right? BD, right? Is it right terminology? BD, block description, right? So you have the some linked list description of block descriptors, right? In main memory. So you have to prepare that block descriptor in main memory. Then start DMA operation. Then block descriptor will be coming in through that connection, right? And this DMA engine will DMA operation, right? So I was asking that, hardware software interaction, right? So, that is, very important, not only this, not only for this question, but for the embedded system design, because, embedded system design involves, the design of both hardware and software. Right? You have to design both hardware and software, right? So then, there are very wide spectrum of issues you have to consider, not only from hardware design, but how software is accessing the hardware, right? So, for example, the page table. If you are interested in virtual memory and TLB interaction, right? Page table is set up in main memory, and that page table will be cached in TLB. That interaction. Also interrupt, right? So you have to have some good understanding what you have to do in software to process interrupt, right? To understand that, you should have very strong understanding of what hardware is doing, what CPU is doing to process interrupt, right? That kind of interaction, right? Because again, embedded system requires the design of both hardware and software. And in this class, we are trying to address, many different, very wide spectrum of, the hardware software detail. For example, we are talking about what? We are talking about, hardware design from scratch, right? Like the 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 reference design, I gave you, right? The Guyun did the camera interface to VGA, the design from scratch, right? And we are also taking IP-based design approach, right? Intellectual property, hardware IP. So using Vivado, we are instantiating some IP, component. Someone built that IP component, right? Then connect them together to create small embedded system, right? And also we talk about, we briefly talked about assembly programming, right? I gave you one just very small example of assembly programming, ARM assembly, to turn on LED, right? Using GPIO, right? You use store instruction to access GPIO component, then you are able to turn on, turn off LEDs, right? And also high-level language, right? You are using C, code, C language, for software programming, right? So we are in this class, we are trying to address, very wide spectrum of the embedded system design, right, issues, right? So you have to have, very clear understanding of that distinction between, hardware and software, right? Sometimes some of you are very, confused with, what you have to do in software to access, hardware component, and why you have to do that, right? So, by using this example, I was trying to emphasize that aspect, right? So that is one thing, midterm exam. And second, yesterday I emailed you announcing class project, right? So class project, click on this. That is about the systolic array design in the example CNN, convolutional neural network model, right? So that will be discussed in the next class in detail. But that is class project, which is due 6th of November. Okay, so you have little more than 1 month. Okay, for that project. So let's check our upcoming schedule. Okay, so we are here 2nd of November. Then I think I'll give you lecture until 9th of November. Okay, so 2 more classes. Okay, 2 more classes excluding today's class. Then it's all yours. Your project presentation and project presentation, paper presentations and project presentations, right? So I'm thinking roughly 3 weeks for paper presentations, starting from Thursday, okay, 11th of November to 2nd, or okay, depending on your progress, okay, 30th. Okay, so roughly 3 weeks for paper presentations, and then 2 weeks for project presentations. Okay, project presentations. That is the schedule I'm thinking of. Okay, any question about this? Then during your presentations, I'm going to be very silent. Okay, I'm not going to say anything. Okay, it's all yours. Okay, I'll talk until Tuesday. Okay, Tuesday, November of 9th of November. Okay. Okay, then we have to, I guess, we have to fix the presentation order, right? Paper presentation. So let's play this game to find out the presentation order. Okay. So okay, your number, right? Guyun, you are the number 1. Dongwoo, you 2. Okay. So what do I have to do? 1. Okay. So what do I have to do? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then what? Then presentation order. Same 1, 2, 3, 4. Confusing, right? First, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11s, 12s. Okay. Okay. So that is the one. Let me screen capture. So that means Guyun, you are the number one. Okay. Guyun, you are the number one. And second is who is second? Okay, 4. Dongwon, you are number 2, and so on. Okay. So let me just hold that. Let me scroll that. Okay, here at the end. Okay. So 2 presentations one day. Okay, 2 presentations in one day. So that means 11th, right? 11th of November. Guyun and Dongwon. Okay, you 2 guys should give presentations. Okay, so roughly 30 minutes, I guess. Roughly 30 minutes is okay. 30 minutes for each presentation, and 5 minutes Q&A about that. And little warning, warning or asking is that when you give a presentation, do not translate, English into Korean, right? Papers are written in English, right? Do not translate that English sentence into Korean, right? That means you have to fully understand what they are proposing, right? What they are evaluating, right? Their evaluation. Then try to use your own language. Okay, use your own language. Do not say, "Oh, that guy said that." Okay, you have to use your own language. Okay, then it's like your paper. Okay, not their paper. It's your paper, right? You proposed, you wrote that paper, right? So you have to present that way, okay, using your language. See what I'm saying? Okay, Dongwon, Guyun, see what I'm saying? Okay, use your own language. Do not just interpret English into Korean. That is a really bad way. Okay. Okay. Any question? Anything you want to add? Suggest? Predict? Speculate? Anything you want to say? Okay. Let's get started today. Then today I'll give you a short introduction to DNN implementation options. Okay, short introduction to DNN, deep neural network implementation, hardware implementation or software implementation, all combined, software, hardware combined, right? That implementation options. Let me try to explain briefly. The slide, this PowerPoint has 49 or about 49 slides, but first half is very basic stuff, so we can fast move forward. Okay, so that is pose estimation model. Okay, using pose estimation model, you can tell, right, what this guy is doing, right? So that is one the neural network example. Okay, so let me do this. So abstraction, you can skip this. Right? You can skip. Also this one, basic stuff. How about this? From transistor to some hardware component, some meaningful hardware component. So transistor is just a switch, right? So based on this switch, you can create logic gate, NOT gate, OR gate, NAND gate, flip-flops, and so on, right? So using these logic gate, you can create something more meaningful like multiplexer or ALU decoder. So by combining these components, you can create something wonderful like CPU, right? That is a transistor count according to years, right? That number of transistors on the same silicon space will be doubled every 18 months. Famous, Moore's law, right? So if you look at the most recent data, looks like this. If you look at how do you read this number? 5 billion, right? 5 billion. In Korean, 50억, right? 10 billion, 50 billion, 500억, right? 100억. Number of transistors, right? And then look at this. Apple A13, Apple A12X Bionic chip that contains roughly 7 billion transistors. What is 7 billion in Korean? 70억. Right? 8 billion, 7 billion, around that range. That means, so how many is that? That 7 billion transistors. How many people live on Earth? 7 to 8 billion, right? 7 to 8 billion people. So that means on this nail space, this small amount of nail on this small space, Earth's population was transistor lives, okay, on this small space. So it is amazing technology, right? How small transistor is, right? How small. So transistor. So we are talking about these days. We are talking about 7 nanometer technology, right? And 3 nanometer technology, right? So that is a transistor size, a channel size. So if you compare that number against this red blood cell, look at this, 7 micrometer. 7 micrometer versus 7 nanometer. So 1,000 times smaller, right? Transistor is 1,000 times smaller than red blood cell, right? Super small. And frequency determination. How do you, after designing digital logic, how do you determine operating clock frequency? So based on critical paths, right? So in this simple example, you have 4 flip-flops, and there are 4 different paths from first flip-flop to that flip-flop, and from here to bottom, right. Okay, so from left bottom to this one and to here. So 4 different paths. So among those 4, the clock frequency is determined by the longest, the path, right? Critical path, in other words, right? Whichever is longest, 1, 2, 3, 4, that determines clock frequency, right? So there are a lot of flip-flops in digital logic. Okay, so very basic stuff, right? If you compile a C code, then object dump it, then you get these instruction and machine code, right? Instruction machine code. The reason why I say this instruction and machine code is because NPU, neural processing unit, NPU is taking the same approach actually. NPU. If you look at the neural processing unit inside your smartphone, then it is implementing some instructions, like convolution instructions, right? Pooling instruction, okay, and some non-linearity, RNet, operation and so on. So by combining those instructions, you can write software which is able to run convolutional neural network. So same approach, right? Instruction. So NPU is implementing some instruction, right? So compared to this, this instruction, you can call this very coarse grain instruction. It's a very fine grain instruction. that no one is using that terminology, but my feeling is very fine grain, right? Microscopic, still microscopic, but fine grain, very coarse grain operation. So instruction and machine code, right? And memory location. So I think I can skip this. So based on pro and counter, right? Pro and counter is pointing the location where instruction is, patched, right? So location 0, first instruction coming in, CPU execute, right? And that is repeated forever. Okay, skip this. This one also, elementary stuff. 32-bit architecture, 64-bit architecture. That is talking about data paths, right? Inside the CPU, right? 32-bit, it is able to process. So that is basic unit of data processing. Basic unit of data processing. So 32-bit CPU is able to able to take two 32-bit data and do some processing, right? Taking two 32-bit. This guy taking two 64-bit data and do some processing architecture. Okay, skip this. And SIMD, single instruction, multiple data, right? Single instruction, multiple data. So this one is an example. I think ARM assembly. Using this, instruction, I think V means vector add. So that is R1, R2, 32-bit register, 4-byte register, in other words, right? So each rectangle is 1 byte, 1 byte, 1 byte, 1 byte, 1 byte. So I8, right? 8-bit operation. So if you execute, this instruction, so it is a byte addition operation, byte by byte, right? So this adder is taking the first byte from R1, first byte from R2, and give you output, right? This adder, right? 4 different adders, taking 8-bit each, 1 byte each. Right? So single instruction, multiple data, right? You run single instruction, but you are able to process multiple data. In this case, 4 data, right? SIMD. So that approach is useful for DNN data processing, DNN, because you have to do a lot of multiplication operations. Not just one, a lot of, right? Billion multiplication operations. So if you implement SIMD instruction inside the CPU, that can be, used to speed up DNN processing. Right? So SIMD concept, okay. And floating point operation. Computer is able to process two, kinds of data. First one is integer. Second one is a real number, right? Real number. That is floating point, number, right? Real number. And to represent this, floating point local variable ABC, float, right? In C, data type. We are using 32-bit, okay? 32-bit for each local variable, A, 32-bit, B, 32-bit, C, 32-bit. That format. IEEE 754 format, right? First one is a sign bit, right? Then 8-bit exponent. Then the remaining 23 is mantissa. So for that operation, so actually the floating point operation is super complicated from a computer point of view. So it is not like integer, right? Integer operation, you need just simple adder, right? But floating point operation, think about this, addition 6.5, 3.5. How do you store that number in memory first? 6.5. So you have to convert that number into this scientific notation like this. Then based on this format, you have to fill, these bits. Okay? So this positive number, right? So 0, sign bit. And then exponent is 2. So, and you have, according to that standard, you have to add 127 127, I think, 127. 127, right? Plus 2. If my memory is correct, the 127. That goes to exponent, right? And then 101, so excluding first one, right? 101 goes to this mantissa field, right? So computer stores that number, 6.5, with this format. Then what computer is doing? Computer is reading this data from memory. CPU, right? CPU is reading this data from memory. Then separate sign bit, exponent field, and mantissa, right? Then for that addition operation, right? CPU, this floating point unit, okay? Floating point unit is comparing this exponent first, right? 2 and 1. So exponent is different. So you have to make it equal, okay? By shifting, either this or that. And then after that, you can add something, right? So it is, very complicated operation, the floating point, right? And for, DNN training, typically, right, rule of thumb is we are typically use 32-bit floating point numbers. Two different things in DNN, right? First, training, right? And inference. So for training, we are using 32-bit floating point. And for inference, we are using 8-bit integer. That is people typically use that, these two, right? So for training, this one, inference, 8-bit. That is why I brought up this format. Okay, then power issue. So I think let's move on. Okay, power issue. And power consumption is proportional to frequency and proportional to voltage squared. Okay, voltage squared. If you increase frequency, then power dissipation will linearly increase. If you increase voltage, okay, the operating voltage, then power goes up, okay, dramatically. That is one. Okay, probably move on. So this slide, I'm trying to show you this data. How many transistors? 1.75 billion transistors. 1.75, right? 17억, right? 17억 transistors. And cache size 8 megabyte. 8 megabyte cache. And Apple M1 application processor. Right? I recently bought that the iMac, which include this application processor M1. So that is Apple designed application processor, right? And Apple is using ARM instruction set. These CPU, okay? Those are ARM CPUs, right? In-house, Apple homegrown CPU, okay? And one special thing about Apple M1 is it has neural processing unit, NPU, okay? For DNN, the processing, okay? You have DNN. So this one, Guyun, can you please read this?
Focus on computer architecture. Semiconductor technology, programming language, programming model, EX, transactional memory, virtualization, security, operating systems, application, computer architecture.
Okay, so in the past, 40 years ago, when computer was first introduced, right? Intel, right? Intel, IBM, they designed, central processing unit, CPU, and software companies, right? Software companies follow the specification. That means, the Intel is providing so software architecture reference manual listing all the instructions Intel is providing, x86 is providing, right? And using those instructions, a software programmer designed, something, right? So the hardware first, then software next. That approach. But these days, software guys are requesting something to hardware vendors, right? To Intel. Okay, for example, security. For security, Microsoft is demanding, okay, we need AES algorithm processed fast. So can you provide AES instruction for me? Intel says no. Okay, I can talk to AMD, right? Then Intel has no choice, right? And virtualization, right? Virtualization technology too, right? At the beginning, right? Intel processor did not have support to virtualization. Then there is a need. So Intel started to add some, VM, enter, VM, exit, that kind of instructions, right? And also, these days, AI, right? AI, uh, uh, AI is exploding, right? AI applications are exploding, right? Many people want to run a DNN model in computer. So computer architect is trying to add some hardware support for that application. So it got reversed, right? Application and software companies are demanding computer architect to add something, right, to run that application fast, to efficiently, right? That is the one. Okay, Mingyu, can you please?
Imagenet challenge, image classification, 1,000 classes, and 1.3 million training set.
Okay, I think most of you have heard about this Imagenet competition, right? It started roughly 10 years ago, 2010, 11 years ago. Right? So what it does is, it is providing, providing some images like this, okay? And DNN model supposed to say, okay, this is a steering wheel, and this is a knife, this is a shoes, right? So there are 1,000 different objects in the image, right? And by training a DNN model with 1.3 million images, after training, DNN model with that many images, the model supposed to say, supposed to recognize the image and tell, okay, this new image is knife, the new image is shoes, and so on, right? So if you look at this graph, so accuracy, right? Look at this. Top 5 error. The human accuracy, human error 5%. Okay, 2010, it was like 28% error rate. But if you look at this ResNet model, okay, it performs better than human, right? Human is 5% error, but this one is even lower than human, better than human, right? But very complicated model, right? ResNet. In this class, we are going to focus on convolutional neural network that is used to recognize images. Right? And CNN, that is the typical step you have to take to classify the image, right? Car, truck, and so on, right? And then CNN can be CNN. There are two big steps. The first step is what? feature extraction. And second step is classification. So what do you mean by feature extraction? Based on this image, input image, you want to get okay, this feature, okay, left top corner, you have some curve, right? And right, left, right top corner, you have also curve. And here you have circle, that feature. Okay, you have some square right here, square. Okay, those features. Okay, at the end you want to get those features, and based on these features, 특징 in Korean, you want to tell. Okay, that is car. Okay, that is truck. That is van. Classification. So again, two different stages. First stage, feature extraction. Okay, feature extraction through convolution operation. And then based on those features, based on these features, right? Based on these features, you want to classify that is car, that is truck, or airplane, and so on. Okay, so that is typically fully connected network. Okay, so convolution operations, okay, in general, convolution operations and fully connected. Okay, so convolution operation is very simple. Okay, that is example. So you have input image, for example, this one, input image, each pixel information, and this one, small 3 by 3, that is filter. Okay, so by going through this the input image source with 1 bit, 1 pixel shift, you are doing multiplication, and addition operation, make, right? You are multiplying this first pixel with first value in filter. 0 multiplied by 4, 0 multiplied by 0, 0 multiplied by 0, and so on, like this. And output will be stored, right? That convolution operation. So operation itself is very simple, right? But you have to do a lot, super humongous amount of multiplication, right? Multiplication and addition. Okay, and this one, Dongwon, can you please?
Software libraries optimized for matrix multiplication. OpenBLAS, Intel FKL for CPUs, CoBLAS, cuDNN for GPUs. Shimmed single instruction multiple data to do make multiply accumulate in parallel in CPUs and GPUs.
Okay, convolution operation, right? Again, this one, you can think of it as input image and filter. Okay, filter. And 2 by 2, right? 2 by 2 filter, 3 by 3 input image. And you do convolution, right? So these 4 pixels, right? This one and filter. You get first data. And one pixel shifted. So 2, 3, 5, 6, that input image, then filter, convolution operation. Then you get this 2 something, right? And that convolution operation can be converted into matrix multiplication. This convolution, okay, 1, 2, 3, 4, 1, 2, 3, 4. This position, look at this, okay, 1, 2, 1, 2, 1, 2, 1. Sorry, this row and this column, okay, 1, 2, 3, 4, 1, 2, 4, 5, right? 1, 2, 4, 5. So input, right? 1, 2, 1, 1, 2, 3, 4, 5, 6. That position, pixel position, 1, 2, 3, 4, 5, 6. So that input, and you have what? Filter. 1, 2, 3, 4. 1, 2, 3, 4. So you are doing convolution with this and this input image. So 1, 2, 3, 4. That okay. Then 1, 2, 4, 5. Right? 1, 2, 4, 5. Okay. Multiplication. This row and this column. Right. So the point is, convolution operation can be translated into the matrix multiplication. Okay. The reason why we want to do this matrix multiplication is because we want to use, software library. Okay. There are very well, designed software library for matrix multiplication in, like this Open Plus, Intel MKL. Okay. If you want to use CPU for matrix multiplication, you don't want to write matrix multiplication from scratch. Very well designed libraries there. You can just use those libraries. The thing is, this library is trying to use, memory hierarchy, cache, hierarchy, locality, trying to optimize for some specific, architecture. Okay. So again, the reason why we want to convert convolution into matrix multiplication is because we want to use those libraries. Okay, those library is very optimized, right, for some, the CPU, the memory hierarchy, right? Cache hierarchy, and also you can use if you want to use software, right? Then you can use SIMD, single instruction, multiple data, for that MEG operation, multiplication and accumulation operation. Not only in CPU, right? GPU is very specialized, right? It has abundant, very super large number of functional unit. Okay, you can use a GPU also. Also, not only convolution, but the fully connected. Okay, so if you go back, not only convolution, but fully connected. Okay, second step, that can be represented also with matrix multiplication. So input, okay, fully connected, right? So you have feature, you have some, features. Then after going through this fully connected, you want to get this output. You can have multiple outputs, right? Depending on the classes you have, right? So that is called the weight, right? So this one, okay, this one is an example, okay? So some equation, sum. How do you get sum? You do multiplication of, okay, there is multiplication. X is multiplication. X and this weight. Okay, X1 and weight 1 multiplication. X2, W2, weight 2 multiplication, and then addition, everything. So that can be, this can be represented with that matrix multiplication, weight. Okay, then input, weight, right? Weight, input, and bias. So once you represent this fully connected layer into a matrix multiplication, you can use software library, right? Well designed software library. And this one, systolic array, that is a class project, right? Now, hardware implementation, right? Instead of using software library, we want to design custom hardware, which is very, efficient in matrix multiplication, right? So this one is an example. Assume that you have 4 by 4 matrix, okay, multiplication. Then you have to do, right, A00, B00 plus this one, and so on. Then you get C00, right? So systolic array, this is an example of systolic array. You have same processing element PE. Okay, arrange it in this way. Okay, same processing element, arrange it this way, and each processing element is doing make operation, multiplication and accumulation operation. And important thing is you have to supply data in this way. Okay? So that is highlighting this one. A0 first row here, first row, and that column. Okay. Okay. Then so that is the clock boundary. Okay, this green dot line, that is clock. So let me draw clock, clock signal like this. So clock number 1, number 2, number 3, and number 4. So in clock number 1, that first data is shifted in to first processing unit, processing element. And in the same cycle, the first column data B30 is also shifted in. So this unit is doing multiplication. A03 multiplied by B30. Okay. So everything is shifted, right? So you are shifting. First clock cycle, that whole information is shifted in. Okay. And that also information, this vertical column data also shifted in to the bottom, right? And clock cycle number 2, A03 is moving to second map, right? And A02 is coming in to first PE. Okay, so a little confusing, right? So you can draw, right? You can draw the data movement, right, according to the clock cycle, right? And the same clock cycle number 2, think about this column, right? B30, first 30 was here, right? B30 was here, and it is moving down to this second MAC. At the same time, B20 is coming in, right? Think about that, a little confusing, but if you think carefully, not that first PE, okay, first, okay, first PE, right? You have 4 PE. So that guy is doing what? The guy is doing A03 multiplied by what? B30 in clock cycle number 1. And clock cycle number 2, that is stored in accumulator. It is MAC, right? Multiplication and accumulation. It is stored inside here. Okay. And then clock cycle number 2, it is doing what? A02 multiplied by what? B20. And that is going to be added with this information. So you are doing addition, right? Clock cycle number 3, what is done? So A01 is coming in, and B10 is coming in, right? Plus A01, B10, right? So first PE is responsible for computing this C00. Okay, and second PE is responsible for this C01 and so on. So if you keep doing that operation, so it takes 1 clock cycle, okay, 2, 3, 4, 5, 6, 7 clock cycles to compute all 16 output, right? 1, right? 1, 2, 3, 4, 5, 6, 7 clock cycles to compute all 16 output. Think about that. Right? So that will be a class project. So class project, I'm asking you to. So in this case, we have two convolutional layers, right? First, look at this convolutional layer, another convolutional layer. So I'm asking to convert the first convolutional layer implementation into convolutional layer using systolic array. Okay, that is the class project. Oh, any question about this? Okay, let's move on. Then non-linearity, that is the step here. So after convolutional layer, you go through this some non-linear function. Okay, non-linear function like sigmoid, ReLU, and some other things. So in our project, we are going to use Linearity for handwritten digit recognition, right? 0, 1, 2, 3, 4, 5, right? Handwritten that digit recognition, Linearity. Okay, so Linearity is using that ReLU activation function. And hardware implementation, from hardware implementation point, very simple, right? The output is negative, 0, right? Output is negative, then, so sorry, input is negative and output is 0. Input is positive, then output is same as input. And pooling layer is also very simple, right? So there are two different max pooling, average pooling. The thing is, you want to reduce the resolution because you want to handle. So you don't want to handle, right, full resolution output, right? So 640 or VGA 480, right? That the pixel number. Okay, there are too many pixels, right? So you need to reduce the resolution to generate final feature map, right? Because you don't want to have too many final feature map, okay, to fully connected, okay, or fully connected layer, right? So you don't want to have 640 by 4080, for example, that many feature map. You want to reduce the number of final output, reduce the resolution. So in this case, you want to reduce that to half, right? Quarter actually, right? So the 2 by 2 becomes the 1. So max pooling. So among these 4, you want to select the biggest, largest number, right? So 9 max pooling. Average, right? You want to average out, right? 2 plus 9 plus 4. Divide by 2. 4, sorry, 4. Okay. So average. What is the average? That number, right? Do you know what pooling method Linearity 5 is using? Our Linearity code.
In Linearity, we use max pooling.
Okay, we use
I
max
think.
pooling, right? Linearity. Okay, max pooling. Yeah. Okay, thanks. Okay, then let's talk about the TPU. Okay, that got famous because of that competition, right? So AlphaGo. And then I think who is presenting this paper? TPU. Who selected that paper? Soon, you selected? Okay, probably Seung-Hoon will explain in detail about that. But look at this block diagram of tensor processing unit. First people use different names to refer to the similar component, right? Some people use NPU, right? Neural processing unit. And some people use DPU, right? Deep. What is that? What does that stand for? Deep neural processing unit, or I don't know. DPU, right? Some people use Google, right? use TPU, tensor processing unit. And some people use neuromorphic, right? Neuromorphic, even though neuromorphic is a little bit different, right? It is using some spike, I don't know, spike model, I don't know. So anyway, different names to refer to similar component. Google tensor processing unit. What is tensor? So Google, what is tensor? Guyun, you are a math major, right, in undergrad.
저도 정확히 텐서가 뭔지 그 딱 알고 있는 거 아닌데 매트릭스 같은 그런 형태의 데이터 집합이라고 알고 있습니다.
So my understanding is multi-dimensional array, multi-dimensional array. 2-dimensional, 3-dimensional, 4-dimensional array, right? Tensor, right? So tensor, that tensor processing unit. So take a look at this block diagram. So you have that goes, if you have a TPU board that goes into PCI Express slot, right? PCI Express, right? So you have PCI Express, okay, slot, okay, by 16. You have 16-bit data bus, right? And then look at this. So look at this matrix multiplication unit. Okay, so matrix multiplication unit. How many? 64K. So 8-bit data processing, right? Uh, 256. I think 256. I'm not sure, but someone can present next time. 256 by 256. If it is implemented in systolic array type, array way, right? That is 2, 8, 2 to the power of it. That is then 2, 16, which is 64K, right? Okay, that many multiplication and accumulation unit, MEG operation. So every clock cycle, so it is able to do, right? Best case, right? It is able to do 64,000, right? 1,000 is 1024, right? 1024. 64,000 multiplication operation every clock cycle, right? If you fully utilize that unit, every clock cycle, it is able to do that many different multiplication operation. Think about CPU. CPU, right? CPU, you have one multiplication unit. Every clock cycle, one multiplication. Versus here, TPU, and many multiplication every clock cycle, right? And some buffer, unified buffer to store what? Store, activation, input activation, output activation, input image, and output, processed image. Okay, input activation, output activations. How big? 24 megabyte. Think about that. How big your cache in x86 computer these days? 8 megabyte, right? Let me check my computer. Check my computer is pretty brand new. It is 10th generation. 10th generation Core i7-10, right? 10 something, right? And how many CPUs? 8 cores, physical cores, and 16 logical cores, right? Thread, 16 logical cores. And then check out cache. How big? 16 megabyte. Okay, 16 megabyte. Compare that, right? You have 24 megabyte on-chip buffer. Not only that buffer, okay, also accumulator, 4 megabyte here. So multiplication unit and activation, right? Activation hardware unit, ReLU, right? ReLU, right? And also pooling, right? Pooling unit. So it is going through multiplication, activation, pooling. So that is, one convolutional operation, right? One set of convolution operation, right? Then it goes back, right? So using that, you look at this systolic data setup. Systolic data setup. Data setup is what? This setup. You have to set up data this way. You have to provide data this way, right? Data setup, right? So that is rough. Okay, this one is input data. Input data goes to matrix multiplication unit. Then here, look at this, weight information. Okay, some filter information. Okay, filter information. In fully connected weight convolution, filter information. And then who is going to read this? Dongwoo, can you please?
Read host memory. Read data from CPU host memory to unified buffer. Read weights from read weights. Read weights from weight memory into weight 50 as input to matrix unit. Matrix multiply, convolve. Perform a matrix multiply or a convolution from the unified buffer into accumulators. Activate. Perform the nonlinear functions such as ReLU, sigmoid. Write host memory. Write data from unified buffer into CPU host memory.
Okay, thanks. If you read TPU paper, it says TPU is providing those different instructions, key instructions. Not only this, but those are key instructions. Look at this. Read host memory. Read data. For example, image, input image from CPU, host memory to unified buffer. PCI, through that interconnect, through that PCI Express, from main memory to host memory, right? Main memory to here, unified buffer. So that instruction is storing input image, for example, input image to unified buffer, and also read weight instruction. So read weight information into this buffer from here. Look at this, DDR3, right? No, this is not main memory, right? Okay, anyway, okay. So read weight, okay, into weight 54. Okay, and third, matrix multiply instruction or convolution instruction. Matrix multiplication or convolution, that is doing matrix multiplication with this data input and the weight. And activation instruction. Right? Activation instruction is doing that ReLU kind of operation, right? Using that hardware component. And then the result can be written back to main memory, right? Written back to CPU host memory. So TPU is like hardware accelerator, right? Co-processor. CPU is passing the image you have to process, then output is stored back, okay, from TPU to main memory. It's like co-processor, right? And according to the table, according to paper, look at this table. It is comparing the performance of the TPU against Haswell, fourth generation server processor and NVIDIA, okay, GPU. No number, but look at this, 92 tera operation per second TPU. Whereas in Haswell server processor 2.6. What is tera operation? Tera operation 2.6 tops. Tera operation per second. Tera 10 to the power of 12. How do you read that number in Korean? Billion operation per second is, if the billion, next number is tera, right? Billion tera operation. Billion means 10억, right? And tera is what? 1조, right? 2.6조 operation per second. Every second, 2.6조 operations, meg operation, right? Actually, not just meg operation, but addition, right? Multiplication and addition, meg. So 2 operations, right? So actually 48. Sorry, divide by 2. 46 meg operations. 46 tera meg operation per second. Something like that. Okay, let's switch it to, so that is used in server system, right? TPU. How about embedded domain? Okay, this one. Kyungchul, can you please?
Our first micro NPU launched in February 2020, designed to tightly work with a companion Cortex-M, 32 to 256 megs, configurable, 0.5 TOPS with 1 GHz, weight decoder and DMA for on-the-fly weight decompression.
Okay, thanks. NPU, micro NPU, okay, small scale NPU that is tightly coupled with Cortex-M. Cortex-M is microcontroller, right? That is used in very low power, low performance electronic devices, microcontroller, right? And it is tightly coupled, right, with Cortex-M, and introduced last year. And it is configurable. If you have a license, you can have 32 meg or up to 256 meg. Okay, here. Then if this guy is running at 1 gigahertz, then NPU performance, best performance will be this one. Assuming that you have this many meg, 256 meg unit. Okay, the meg is your 2 operations, right? Multiplication and addition. So 512 operations. So if you do multiplication, then this number 0.5 tera operation per second. Okay, if it is running at 1 gigahertz. Okay, so that because the AI, right, DNN processing is so very widely used these days, right? People want to integrate. People want to run some DNN even in IoT devices, small microcontroller, right? That is because there is low power. Okay, you have only 1 meg, then you cannot do anything useful, right? Okay, some more information about that NPU. Okay, this one, Himin, can you please?
Compiler generates command string. DMA controller. Read neural network description containing command string, base, bias, scale info. Transfer IFMs, OFMs, and intermediate data in system memory.
Yeah, so this NPU is also taking same approach, right? It is implementing instruction or command, right? That command is, by combining those commands, you can run some DNN, you can implement some DNN model, right? So it's like, if you go back to here, then look at this one, TPU, instruction, right? Instruction stream. So those instruction streams. So by mixing these instructions, you can implement DNN, some ResNet, for example, DNN model, right? Also here, same thing, right? Using command stream, right? Some example is this. I managed to find some instructions, command, right, like this. OFM is output feature map. Output, right? You have input image, then convolution. After going through convolution, you have output, right? Output feature map. And input feature map is input input image. And corner is, for example, corner is filter, right? Filter. So here you want to do this one, input tensor, input multi-dimensional array, right? 8 by 8 by 16, right? Then filter 2 by 2 by 16. And you have 16 of them. 16 of them. You have 16, this guy, 16 different filters. Each one with 2 by 2 by 16. Okay. Then you get, this output. Stride is how many pixels you are moving. 2 by 2. Convolution moving 2 pixels. 2 by 2 pixels. Right? So on. So this slide I'm trying to show you, right? ARM micro MPU is also implementing those different instructions. By mixing those, you can implement DNN model. And this one is the graph from the survey paper. This survey. And it is showing many different DNN implementation. According to power consumption and performance. And they classified DNN accelerator into 5 different categories like this. Low power, embedded, and so on, data center, and so on. Okay, they categorize the DPU into 5 categories. Here, very low power, right? This one, very low power example. You can just skip. You don't have to read. Okay, and embedded domain, ARM ethos. And then one special thing about this slide is this one, I think, right? Sphere video processing engine, this one. Okay. It doesn't disclose some detailed information, but it says it is implementing PIM, processing in memory. Okay, so that is, I think, a special thing. So in memory, right? In memory, you have not only storage cell, right? Storage cell, but also you have a logic unit to do some multiplication operation. You don't have to read the data, right? And let CPU to do multiplication, right? The data stays in memory. Okay, stays in memory, and you can do simple arithmetic operation yourself. Okay, so in that way you can avoid data movement from memory to CPU, because that is very expensive. Data movement from memory to the CPU. Okay, that is not only taking time, but also power consumption. So by taking this approach, okay, it has advantage in both ways. Okay, some example, right? MPU. Okay, Samsung, okay, Exynos has the MPU implemented, and it has 1024 meg. So every clock cycle, if you fully utilize meg, then you can do that many meg operations. And then these 5% of real estate and the price, the NPU price, okay, NPU. And A12 Bionic chip, Apple iPhone, it has also NPU, right? And performance is a little bit better. So it came out 2019, 2018. Performance is better. 13, okay, so even more. Right? And in our lab, we are doing some research. We are doing some research with Lec15, and we are using the reference SOC from this group, ETH, Swiss ETH research group. They they opened their implementation, SOC implementation called Perpissimo. Okay, and Perpissimo has a Lec15 implementation, RISC-V, not only RISC-V CPU, but many different IO devices. Okay, and then the reason why I brought up, I include this is they are actually implementing DNN model using. They they are providing special instructions. Perf, they are providing special instructions for DNN acceleration. Okay? For example, this. If you know RISC-V, RISC-V is the open source instruction set architecture, right? So free. It is free of charge. Everyone can use RISC-V, and it is based on that. It is based on some extension, instruction extension, not based on. So it is providing base instruction called RB32I. It is base instruction, and you can add any extension, instruction extension, ISA extension, your own ISA extension to this RB32I. And for extension, they implemented this special instruction for DNN acceleration, for example, shuffle. Okay, so this example, you want to do 5 by 5 convolution operation here. Okay, so let me show you. Okay, so convolution 5 by 5. So original input image, then filter 5 by 5 filter. Okay, so after this convolution operation, this filter is moving down 1 pixel like this, right? From here to 1 pixel down, and then the input, right? Input image you need to process is that data. Okay, from this to that data. So almost all data you can reuse, right? But those are new. 26, 27, 28, and so on. Those are new, right? Somehow they want to create. They want to efficiently, arrange the data you want to process. Okay, the shuffle instruction is efficiently rearrange data. Okay, so from here, register, CPU register R12 to here. So using shuffle instruction, you can create that data. So details probably you can take a look at this paper. Okay. So the point is they implemented special instruction for efficient data rearrangement. Okay, think about it. If you don't have this special instruction, you have to use many different instructions to rearrange this data like this. But using special instruction, that can be done in one instruction. Okay, so last slide. So there are probably many different design choices from CPU to ASIC. Pure hardware implementation, pure software implementation, right? So the performance, so pure software implementation is very good from flexibility point of view. Okay, if you implement everything in hardware, the performance is the best. Okay? Performance point of view, this one is best, but it is not flexible. So people use MPU approach, right? It is providing instructions. By mixing those instructions, you can run any different DNN models, right? So some spectrum, some software to pure hardware. So in between, you can implement some special instructions like SIMD and also the shuffle instructions. Okay, that is for today. Okay, that is for today. Any question? So next time, I'll show you a demo based on Guyun's implementation. Where is this one? This one. But if you are eager to do the class project, probably you can try. Just download the hardware design and follow the instructions. Very similar to what I showed last time, right? So you need to create clock, memory. That's it, right? Clock and memory. That's it. You can run. You can run. You can test. Okay. So with these instructions, and the design is based on, as Guyun said, the design is based on what? This one, CNN. Okay. So that is the source Guyun used. This one, RNet implementation. It's RNet. So again, if you are eager to do class project, probably you can take a look this RNet implementation. Okay. I'll briefly explain that implementation on Thursday and next Tuesday. Okay. Okay, I guess that's it for today. See you next time. Okay, bye. Thanks.